Now let's consider infrared detectors. There are several kinds. First kind is thermocouple. Okay? Thermocouple means you um, have two different electrical conductors, okay, having different energy of electron. Okay, when now you the made contact the end, one end, okay, and then you hit the end, and then there is will be a voltage, the difference at two ends, okay. And another one is a ferroelectric material. And for example, this deuterated triglycine sulfate having permanent electric polarization upon irradiation of IR beam, and this polarization, okay, and changes. Okay, that is called pyroelectric effect. You know, the pyro means heat, electric, effect. So as you know, the infrared light, when one object is irradiated by infrared, and then the object temperature increases. Okay, so using that phenomenon, pyroelectric effect, then you can detect IR. Okay, and another one is photoconductive detector. Okay, some semiconductor materials, uh, the photoconductivity changes upon irradiation. Okay, and upon irradiation, electrons are excited from valence band to conduction band. Okay, using the principle, and you can measure the conductivity change. Okay, and another one, I think that this is the most sensitive detector, the photovoltaic detector. Yeah. Also, the detector is made of semiconductor. Okay, as you know, the semiconductor has p-n junction. Okay, upon irradiation, electrons are excited from the valence band to the conduction band. Yeah, one good example is CMT, mercury cadmium telluride. This the alloy here. Look at that. This this is alloy, okay, and it has band gap, yeah, between valence and conduction band, and this band gap energy is very small, smaller than silicon band gap. You see, silicon is also a semiconductor, and this band gap is about 1.1 electron volt, but this one is much less than that. That means what? You can absorb IR beam, okay, IR now excites electrons from this valence band to the conduction band. As a result, the potential difference is developed. Okay, yeah. And yeah, this is uh, these two detectors, yeah, photoconductivity and photovoltaic detectors are made of semiconductor, and also two, they are very sensitive to IR. But to operate these detectors, you have to cool down, yeah, this detector, yeah, to a very low temperature. Usually, so these detectors are surrounded by liquid nitrogen, okay, to reduce thermal noise. Why? Look at that. This band gap is very small, okay. So the room temperature, mm, the electrons are excited at room temperature. Yeah? A lot of electrons are excited from this valence band to the conduction band. They make electrical noise. Okay, so to reduce such a noise, you need to cool down these detectors. Okay, and then now let's consider the calibrating detector response for luminescence measurement. Okay, luminescence means fluorescence and phosphorescence, mostly fluorescence. Here is a caution. Okay, different detectors respond differently to wavelength. Okay, in absorption or equivalently transmittance measurements, detector responds with respect to wavelengths. light intensity is not important. Okay, you see why? Because usually you uh, take a ratio of incoming intensity with respect to this one, after absorption or after transmission. Okay, this is definition of absorbance, and transmittance is defined by also the ratio of um, exciting the light intensity divided by incoming intensity. All right. So actually, when you measure absorption or transmittance, so detector response is not important. But uh, in luminescence measurement, the story is quite different, because this one, luminescence intensity, is directly proportional to concentration and also to this one, incoming light intensity. Okay, so the detector response quite severely affects the spectrum. Okay, so calibration must be done, otherwise you will get distorted the spectrum. Okay, calibration can be done with certified luminescence standards whose fluorescence has been measured with calibrated detectors. Okay, here, yeah, this example shows how to calibrate. Okay, now let's assume you have two detectors, okay, A and B, and their response with respect to the wavelengths are quite different. Okay, instrument B is much more sensitive than instrument A. Okay, so using instrument A, detector A, you got this signal, this black solid line. Okay, but with instrument B, you got, for the same sample, you got this dotted response. Okay, they are quite different. Okay, so how do we calibrate, to make them equal? Okay, using a standard, luminescence standard, you can calibrate the this wavelength, and after calibration, that is a blue line. Okay, you get the only single the spectrum. Okay, so the point is that for the luminescence experiment, you need to calibrate detector response. Okay? Now let's turn to the optical detectors. They are also widely used. Okay? To understand optical detectors, you have to understand the several properties of light. Okay, in when we learn the grating, and we learned the diffraction. Okay, the light, the property, one of the properties is diffraction. Diffraction is what? The incident angle is not equal to the reflected angle. Okay, for the grooved surface. Okay, on that surface, not only reflection but also diffraction occurs. Okay, now let's consider the refraction. Yeah? Not reflection, this is refraction. here here is the uh, here is the what the borderline between these two what the the material. Okay, and this one the refractive index is n1, and this one refractive index is n2. Okay, and then let's assume that n2 is greater than n1. Okay, and now you send your instant ray, okay, from this side, and now it hits this interface. Okay, and then some of the ray are reflected. Okay, and then um, reflection law of reflection says the instant angle is the same as the reflected angle. Okay, this reflected angle is exactly the same as this one. Okay, this reflection condition is well met when the surface is very smooth. Okay, very smooth. This is very easy to understand. But what about the refraction? Since the refractive indexes are different, instant ray now bent, okay, when it enters another material, yeah, whose refractive index is N2. Okay, now let's say this is a refraction angle theta 2. But don't forget, yeah, in optics, you measure the angle with respect to this surface normal, right? Not with respect to the surface. Okay, so you draw this line normal to the surface, and then you measure the angle. Okay, the Snell's law dictates, yeah, the n1 multiplied by this one sine theta equals n2 sine theta. Yeah, this is called the Snell's law. Very, very simple law. Okay. This table shows refractive index as sodium D line. Anyway, but this refractive angle, it depends on the wavelength. So when you exactly measure the refractive index, you have to use well-defined light. Okay, usually people use sodium D line. Okay, the vacuum refractive index is 1. Okay, 1.0000. Okay, air refractive index is just a little bit greater than 1 because air contains nitrogen and oxygen and other gases. Okay, and water refractive index is 1.33, and fused silica refractive index is 1.46. Okay, and benzene, okay, like blah blah blah. Okay, that means the large refractive index, and then this one, this refraction angle becomes smaller and smaller. Okay, to satisfy this Snell's law. Okay, and here is a very simple example: reflection of light by water. Visible light travels from air, this is the medium 1, and into water medium 2 at 45 degree angle. Okay, theta 1. Here this is now 45 degree. At what angle theta 2 does the light ray pass through the water? Okay, yeah, it's very simple. You know already the refractive index of air and water. Okay, and you know the instant angle, and then refraction angle using this Snell's law. You can very easily calculate the theta 2 of 32 degree. Okay, yeah. And now you can use radians instead of this angle. Okay, instead of a degree. Okay, this part, you know the difference between the radian and a degree. Okay, yeah, this part, uh, I let you read. Okay, study by yourself. All right. Okay, now let's study about the optical fibers. Optical fibers are often very frequently used in spectrophotometry. Okay, in Korean it is called 광섬유. Okay, an optical fiber, it guides light path. Okay, one of the light properties is the to go straight. Okay, it never bends, in ordinary cases. Okay, but optical fiber, yeah, you can guide light from this place, one place to the other place. Okay, although that place is not linearly connected. Okay, the principle is that total internal reflection. Okay, yeah, this is the structure of optical fiber. The core is the made of this one. Now light is passed through this core, mm, and core is surrounded by this cladding. Okay, and the whole thing, the core and cladding, now is covered by jacket. Okay, the important part is the core and cladding. Okay, yeah, this is the illustration. and here this is core, okay, and the outside the core there are cladding. Okay, now light is coming from this side with a certain angle here. Okay, now it hit the this what interface between this one core and cladding, and let's see the N1 is the refractive index of core, and N2 is the refractive index uh, of cladding. Okay, now this incident angle is what with respect to the surface normal, and theta I, and this one, this refractive angle r theta. Okay, and if n1 over n2 is greater than 1, and then all light now reflected inside their core, okay, and then this one reflective light intensity is extremely small. Okay, yeah, there will be a angle for this condition. Okay, you see, so critical angle is defined by theta c equals n2 over n1. Okay, for this total internal reflection, or light is internally reflected, yeah, internal inside the core. Why? Because this one n1 is greater than n2. All right, so that angle is the critical angle, is defined by theta 2. uh, I think this is sine theta 2, right? Theta theta c equals n2 over n1. Yeah, this is quite easy to understand. Yeah, let's look at this one. In this figure now, think about you increase this instant angle. Okay, increase more and more, and then at certain angle, this one, uh, this ray now hit this interface, and then what? And then uh, it gives it is reflected. Uh, let's see. Now, if you increase theta 1, and you also increase the the theta 2, okay, and then now you send the light. You see, the theta 1 is 90 degree, okay, and then theta 2 maybe like that, okay, and then inversely you send the light from this medium 2 toward medium 1, okay, and then within, yeah, within a certain angle, if you send this angle, and then light pass is follows this one, and then it reflected this way, but if you if instant angle from this side is very big, very large, and then light hit this interface, and then this light never, you know, go out to medium 1, but it inside internally it reflected. Okay, and then that angle is called critical angle. Okay, here, so in critical angle, the theta 1 here, one of the angle is 90 degree. Okay, sine 90 is 1. Okay, that's why critical angle theta 2 is given by, I think, the sign must be here. Okay, sine theta c equals n2 over n1. Okay, in this case, n1 is greater than n2. Okay, yeah. So this one, this total internal reflection. Yeah. So extremely small light is leaking. Yeah, but most light is internally reflected. Okay, so if you have this optical fiber, and then as long as you send, okay, this your light, okay, and greater than the critical angle, and then all of your light, yeah, are internally reflected, and then you can send from this side and then other side. Yeah. So this optical fiber is very flexible. Okay, and then you can connect this one end to the one thing and the other end to another one. Okay, and optodes is the is kind of electrode, but optical electrode. Yeah, this is called optical sensor. A chemically sensitive layer is placed at the end of the fiber. Yeah, this is a fiber, and at the end of the fiber, you attach this kind of chemical. Okay, for example, to detect sulfite in food, or nitric oxide in cell, or explosive in groundwater. Okay? And then what? Light now, when it enters this optical fiber, it first what meet this chemical. Okay, now chemical absorbs, or it generates fluorescence. Okay, and then you see the components, the molecules of your interest to detect. Okay, so this way here, now this microsphere with short single strand of synthetic DNA, you attach this one uh, on the surface of this optical fiber, and then you insert this one into your sample, and if there are the complementary target DNA, now it's this one. Mm. So this single stranded DNA now detect this target DNA, and then if you attach this fluorescence labeled molecule, and then now what fluorescence now takes generated. Okay, and then the fluorescence along this optical fiber, and then you can detect. Okay, yeah, that's the principle. Yeah? Rather simple. Okay, here is the fiber optic instrument spectrophotometer. All right. So optical fiber now connected to here. Okay, and then the rest is the same as ordinary spectrophotometer. Okay. Now you have a long optical fiber, and then at the end you um, you made the fiber as optodes or optrode. Yeah, and then the detected signal. Okay, now passing through the optical fiber by the uh, total internal reflection. Now it enters this spectrophotometer, and this is diode array. Oh no no, so this is the detector. Okay, so the um, the spectrum is detected by this instrument. Okay, yeah, that's the principle.